The stretch or sway motions are referred as hydraulic actuator or sway motions actuator, and the rotation motion is driven by a hydraulic motor. The output parameters are force. The output parameters are force, speed, or torque, and the rotational speed. Include four parts. Let me first introduce the hydraulic motors. 4.1.1 Introduction and 4.1.2 Operating Principle of the Hydraulic Motors, and 4.1.3 and 4.13 Low-Speed Motors. The popular concept of a hydraulic motor is that it's nothing but a pump run backward. There are some characteristic parameters. Firstly, power and overall efficiency. Need to see have located the input power P PMI of motor. The ZM denotes motor. I denotes the input, so the input power of motors is this equation. This is the pressure and pressure. This is the flow rate. The pressure increase P equals P1 plus P2, and the flow rate is the actual flow rate of the motors. The equals the speed multiplies the area. We introduce each the chapter 1. Do you remember it? And the output power, capital P MO of the motor, can be calculated by this equation. Capital P MT denotes the torque of the motors, and the N denotes the rotational speed, and with the usage of rotational per second. As this term equals the rotational versus the angular speed, which is equals this term. So the output power can be calculated. This expression. The last one, the overall efficiency. Time of the motor is the ratio of PMO to PMI. It can be calculated by this expression, and equals the ratio of this one to this one, and this one can be calculated this equation, and this is calculated this one. So it's also equals the efficiency, the mechanical efficiency multiplies the volumetric efficiency. Second is the torque and the mechanical efficiency. The theoretical torque, can be calculated this form. We have introduced each the angular speed equals this one, and this is the input. This is the input power. The input power equals the output power. So we can get this one. Equals this one, there, and divide this one. So we can get the theoretical torque, and the startup torque. The startup torque can be calculated in this by this equation. This is the theoretical torque, and this is the startup torque. Startup torque equals the theoretical torque minus the loss of the torque, the startup period. So we can get the mechanical efficiency in the startup period. Mechanical efficiency when the motor are in operating condition. So we can get it. Each output, we can get it output. The output torque equals the theoretical torque minus the loss of the torque in the operating condition. So we can get the mechanical efficiency, the operating condition. This one. This is the theoretical torque. So the actual torque equals the theoretical torque minus the loss of the torque in the working condition. The flow rate. Q M, and the volumetric efficiency. The flow rate equals this one. Increase delta Q. Delta Q also denotes the loss, the actual condition in the actual working condition. So the total flow rate equals the total flow rate equals the theoretical flow rate plus the leakage or the loss. Flow rate. The volumetric efficiency in this form, and This is the actual flow rate, and this is theoretical flow rate, which equals the actual flow rate minus the leakage. You can get this expressed. One divide this one equals to 1. Last one is the delivery and the rotating speed. Delivery and the rotating speed. And the rotating speed can be calculated here. This is the delivery. This is delivery, and this is the per storage. So this this one this one is this one. We can get the rotating speed. Working and rated pressures. Working and rated pressure, which means that when the motors are in normal working conditions, we can get its pressure, which means the rated pressure. To classification, motors may be classified based on the working performance. They can be divided into these two categories. One is high-speed hydraulic motors, whose rated rotation speed is beyond 500 rotational per minute. If its rotational speed exceeds this number, it's high-speed hydraulic motor. On structure, the low-speed hydraulic motors whose rated rotational speed is low, 500 retention per minute. High-speed hydraulic motors may be further divided into gear motors. Gear motors to high-speed hydraulic motors, wave motors, gear motors, three motors, and so on. Low-speed hydraulic motors include single-acting radial piston motors, single-acting radial piston motors, and the in-cave multiple-acting radial piston motors. Motors can also be classified as fixed delivery and variable delivery according to their delivery type. So, with another classification principle, we can also classify the motors into the following categories: fixed delivery and variable delivery. Let's compare the graphical symbols between parts. Motors. This figure is the pumps. This figure is the symbol of motors. you can see difference. You can see the difference between the numbers. The symbol is like that. The motor symbol is like that. Okay. The figure 8 denotes the long return constant delivery hybrid motors. Constants delivery hydraulic motors. So that is a low layers. And if it's a variable delivery, there exists narrow. And if means this means it's a reversible hydraulic motor. One is the reversible constant delivery hydraulic motors. The one is the reversible variable delivery hydraulic motors. For 1.2 rating principle of hydraulic motors. Let's have a look at this picture. It's a axial piston motors figure 42. So one is a swatch plate, one is a swatch plate. Two is the cylinder, two cylinder. And the second is the piston. Fourth is the control links. The five is the shaft. So I firstly explained the operating principle. When the pressured oil into the piston, when the pressured oil into the piston, in this direction, into the piston, then you will push the 2 or 3 will push the piston go ahead. And since there is one is the swatch plate, super plate, each move so in the contact point, each will exert a force. Exert a force lend Fn to the piston, and this force can be divided into two parts. In the this direction, it's Fx, and in this direction it's Fy. In the x direction, the pressured oil or pressure, the pressure equals this force, and in this direction, this force can make the shaft rotation. So this is the axial piston motors. This is the operating principle of the axial piston motor. the inverters. Double acting wave motors are generally used in industrial hydraulic system. Here a double acting design operating is illustrated as follows. What we look at the video. Play the video and you can see it. This is the pressure of the oil in going to the this direction and out into this direction. Okay, I'll explain the operating principle. So the pressure of the oil pressure of the oil going to this device in this direction, and since on this is the 4 and 8 and H in this side and this side, the pressure oil, the pressure are the same, but for 7, 1, 3, and H, since the pressure both sides in both sides are lower the same. So there is a pressure differences. So here's the first. This is the wind motors. The structure features for the wind motors. The wings in a wind motors are positioned radially with a zero wing angle. Shutter valve inside is the patch between high or low pressure oil chambers and the wind button to ensure high pressure oil is the wind button that ensure a normal startup. A principle with the preloader is a principle with a principle. Ring with the preloader is mounted at the wind button to prevent the connection of high and low pressure chamber, while high pressure oil enter the wind motor. Wind tank motor are small size in the initial. No share. Making a short reacting adverb for frequently direction, frequently direct change location. Making a short reacting tank and however they have large leakage. They have large leakage and inadequate stable 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 stabilization at low speed. Thus, wind-type motors are applied in small torque, high speed, low mechanical performance requests. Ratio low. Wind-type motors are small size, inertia, but they have large leakage, and so they usually commonly applied in small torque, high speed, low mechanical performance requests. So third one is the gear motors. In the picture, this is the tush. This is the linear. Yeah, the gear. This is the driven gear, and this is the driven gear. So the mesh, the mesh nature. See, see the mesh point. So there are two distances. This one is the A, and this one is the B. So A is the distance from the mesh point to the rod sock. The distance B is the distance between the mesh point to the rod socket. So since A doesn't equal B, so the force are loaded the same for gear one. The force one on gear one pressure multiplies the area and the this wide. This wide is the so it equals this one P and the A1 equals this one, and then check A2. The pressure also P multiplies the this wide, and then multiplies the H minus D. H is the height. H the height of the top circle, height of the top, or the height of the tooth, height of the tooth, height of the tooth. Yeah, this A, this is B. So there are difference between chapter A, between F in chapter 1 and chapter F2. So in the acting in the action of troopers. Here we are. Their motto will operate. Okay, I'll play the video. I'll play the video. You can see it. Flash the oil. Go into the device in this direction and out device. Yeah, 11 here is the driven gear. Each they are matched at this point. Low speed motors. For the low speed motors, which are usually radial piston motors, they have high pressure and large delivery to meet the needs of the low speed rotation, large torque. Because of the large size and the large inertia, they are not suitable for the applications which requires rapid response and frequent direction changing. Those speed motors may be further classified into the following three categories: single acting motors, double acting motors, and multiple motors. So this is a single acting connecting rod type radial piston motors. So let me have a look at the components. One is the case, and the two is system. Three is the connecting rod. The fourth is the current. The current diary indicate volt. Six is the valve shaft. Valve shaft. You can see dash 5. I think 1, 3, 4, 5, 6. 1, 2, 3, 4, 5, 5 cylinder blocks are arranged ideally against the surface of case 1. The point is here, and this against the case 1 with equal distance. The equal distance or equal, the equal distance forming a dart-shaped cylinder block. The pistons Q, yeah, aside with the cylinder block in the back with battery strip. To that rather larger heads with the ladder-shaped surface bearing against the offset ocular of the shaft for central of the land central of the front shaft her O1 or offset with respect to the rotating central of the OOE. Valve shaft, valve shafter 6 have crank ball joined together through a cross key and the rotators with the raft shaft. Pressured oil is distributed to the corresponding piston cylinders by the valve shaft, as shown in this picture. Cylinders 1, 2, 3, 1, 2, 3, 3, cylinders 1 with high pressure oil. Five. So oil and the pistons are subject to high pressure oil, while the other cylinders act with the outlet port. According to the rank and the connected rudder mechanism upgrading, there is a fissure. On each one piston and the bone of the torque against the center of the band axis. The torque P makes the band axis to retort by anti-clockwise direction. The torque on each piston changes with 3 different positions. Thus, the total output torque refers to the sum of torques will locate at the 3 high-pressure chambers of each piston and axis drivers the valve shaft when it is in rotation. So the band axis is rotated continuously with the deploying data changes. Also, the motor will turn in the opposite direction. That's by changing the inlet and outlet port. In this case, the inlet port is 1 and outlet is 1 for V1. run a motor in the opposite direction. This area is the in nature approach, and this area is the outlet approach. So this is the okay. This is the operating principle of the single acting connecting rod type radial piston motors. This equation is very important. We should know how to calculate the delivery for this the delivering for single acting radial piston motors is expressed by this one. This is the area, and this is the offset. This picture offset. This and this is the number of plunger. This is the plunger number. So in this case, the plunger number is 5. Where E is the diameters of the piston, E is the eccentric distance of the crankshaft or the offset, and Z is the plunger number. The structure features for the single acting radial piston motors, they have the advantages of size structure, working reliability, and large size. They are torque position and idle stability and reach low speed. In cave, maybe some problem. 2. The in-cave multiple acting radial piston motors. So there are some components. One is the dialer, and 2 is the rotor. The rotor. 3 is the pistons. 3 is the pistons, and 4 is the beam. 5 is the rolling wheel. The last one, 6 is the valve shaft. Explain the acting principle. Okay, what's the problem? What's your problem? I can't hear you. Can you speak louder? Can't hear you clearly.
I sent you a message in the chat box. Can you check it?
Now, please write down your words in the dialog box. Write down your words.
Yes, I did. I did. You can check.
In case multiple acting radial piston motors, you can see the components, the construction, and the operating operating principle. As shown in this picture, the typical design consists the six components. And the inner surface stator one is composed by multiple identical cable with an equal distance patch, which means these distances are also all the same or they equal the same distance. The number of the cave surfaces equals the acting time of the model. Two identical regions are divided into the concave buttons of each cave. One is the image ring, image zone, or the image region. One for one here and here. Image image zone or image region. The other is the outlet region. Several piston springs are arranged radially among the two with an equal distance apart. The piston's headers contract with the beam wall, which can move freely within the radial grooves of the cylinder block. Rolling wheels 5 on the jollers with the two ends of the beam can roll around the inner surface of the stator. The inner bones of rotor 2 and the outer ocular of the valve shaft 6 match up to allow a sliding behavior of the shaft. Oil distribution port at each bottom of the piston bore is the same as that each valve shaft 6 cylinder. So the valve shaft is stationary, and there are two oil distribution ports on each. Each port having the same numbers. One group of oil distribution port A, port connects with the inlet port of the valve shaft central, while the other group B connects with the returned oil path. These two groups of oil distribution ports are exactly located in the inlet and outlet regions, respectively. Let me do the first. The first the first F chapter FA can be divided into two first and the FT, FT and the FR. The FR The FR are in opposite. The FR are in opposite direction, so they can be balanced by themselves. And the FT, FT here, FT, and the FT is here. In the action of FT, they can FT development a torque at the shaft through the beam. So at, so at the same time, the pistons at the rotunda oil region retract under pressure, and the low pressure oil discharged out through the rotunda oil pouch. This is the operating principle of these multiple acting radial piston motors. So the delivery of this type is expressed as E also below the piston's diameters. Diameter. The S is the piston's stroke. X is the action time. Y is the number of the piston rolls, and Z is the number of pistons in each roll. Okay, we'll take a break for 10 minutes. Okay, we'll take a break.
Yeah, Lawson. Sure. Okay.
Okay, we are continue learning. Continue attending class. Okay. Go on.
Yeah.
And the structural features for the concave multiple acting radial piston. The concave multiple acting radial piston motors have a low torque, have a low torque, have a low torque, have a low torque. Balanced radial force and the largest step-up torque, and can rotator and which means and can rotate steadily at low speed. At low speed. Four point two hydraulic cylinder. It includes four parts. First one is classification and leader structure characteristic. Use the picture instructions and the makeup. So the main dimension calculations. The last one is swing cylinders. So first look at the classification and the speed structure characteristics. Cylinders may be further divided into pistons, piston type, plunging type, and swing type based on their constructions, a single acting, double acting, according to their function. Some typical cylinders are designed as follows. The first one is the piston cylinders. Figure 427 is the double rod piston cylinder. Double what the radius. What is the double rod piston? This is a stationary cylinder band type. And this is stationary piston rod type. So what are branch? This is the two piston rods, two sides of double rod piston cylinder are equal in diameters. It is diameters of equals when input flow rates and the pressures are constant. The output thrust F and speed V are equals in two opposite directions. F and V can be calculated as follows. Since are equals in the same diameters, so the force equals the area. The area is equals this one. This is the difference between P1 and P2. This is the efficiency. So the force is calculated in this way. Since the picture is this area, so the area and is this is so the area is yeah area is equal the area. Area is this is their partial different the emotions. But therefore, so also here is the here calculate this is the flow rate. This is the area. So area is equal to this one. Multiplies the motion, the volumetric emotions. Yeah. So you can get this expression. So for another cylinder, it's the single rudder piston cylinder. You can also play the video. To play the video, the figure 42H. A is the pressured oil. Pressured oil is put into the long rudder. B, the pressure oil is put into the rudder. Last one is the temperature, pressure, the pressure of the oil get into, and okay, totally right. Pressure. Good.
老师，
Okay.
老师, when you share the PDF with us, we can't see the video of this kind of
Oh,
video.
okay,
So
okay,
it will be
okay,
very good if you share the PPT with us. Then we will see this
okay.
picture.
I'll share the
You know?
image.
Yeah, sure. Thank you.
Okay, I have uploaded the PowerPoint, and you can download it. See this video. Oh, for this one, and see how to calculate the force and the velocity. How to calculate this one. This one. How to calculate the pressure oil in image. Calculate that direction. So if pressure is one, the area is A1, the diameter is D. So one, the area is area. This area is here. So we get force equal here. Minus Q multiplies with I. So there exists efficiency multiplies the mechanical efficiency is the force. We can also gauge the velocity to reach by the area. We want the area is A1. A1 area is A1. Okay. There also exists volumetric efficiency, so we can get the A1 here. Yeah, so we can get the speed we want. Okay, and use the same method. We can also calculate this one to get the force, the speed. The last one. So this one, this is the pressure oil, and this is the pressure oil in the outlet region. The area A1, A2, and this is A1. So the force F2, the force F2 equals 1, 1 of the area is here, A1. Plus 2 times A2 also multiply the measure motion speed. A1 can calculate it. A1 can calculate it. 1. A2 So we substitute
Oh,
A1,
Laoshi, can you please write in a white paper because it's not clear.
A2.
Laoshi.
Okay, and can you repeat your question?
Yeah, it's not question. I mean, like, can you write in a white paper because what you written there is not clear.
Right. Okay. Okay. Bye. Okay. Actually, I have typed the equations. Yeah, typed the equations. And yeah, yeah, this one. A1. This is A1 and this is A2 and which we have we had this one. And A1 is here, A2 is here, and the price and the F2 equals A1 plus oh is is depend A2. This is P1. P1 multiplies A2. One, one is here. One is here and A2 is here. So P1 multiplies A2 and minus P2 multiplies A2. Then multiplies the mechanical efficiency and we can get the A A1 A1 equals that's E minus square A2 equals A1 equals square step D and A2 equals square step D minus square D and then we can multiply the motion C. So we can also get the A2 which is also equals the storage area. The area is here. Is the volumetric efficiency. So we can get the figure of what we do. For the last one, this one. the last one is the can also get the F1 and F2. You can get the if we define the ratio of V1 to V2 and the weight. You can calculate the soda case, the pressure and the speed. Feedback. This one can be calculated in the same way, so you can do it by yourself. So the video of the plunging cylinder, the one is the cylinder barrel, the two is the piston with the ring. Sorry. Oh yeah. Okay. The paper and then go to the piston and the put go first. This is note the plunging diameter is D. The input hydraulic oil flow rate is Q. Then the thrust force on the plunging plunger and its speed can be calculated. This equation is the pressure of the so area is here, so we can easily get the thrust force. We can get the speed. It's because the flow rate divides the area and multiplies the volumetry efficiency. So the cylinders of other types. Scopic cylinders. The cylinders shown in figure 4 to 10 and figure 4 to 11 are single acting and double acting telescoping cylinders respectively. Their difference lies in single acting figure, this figure. Figure, this is a double acting telescoping. This is single acting telescoping cylinder. The difference between them is single acting type leads outside force to return to its home position, while the double type accomplishes this by the hydraulic force. The video and you see the differences clearly. Punch go back to the initial at on this there is a third first. Go back to the initial position. The rock piston cylinder. There is a gear. Here. The rock piston cylinder. And go direction. Go ahead and go by. Super cylinder. I introduce the typical constructions and the makeup of the cylinders. Figure 4.2 first construction of the single rod cylinder. So one is the cylinder bed, the two is the cushion piston, three is the complete key, 4, 6, 4, 6, 10, 12 is seal, 4, 6, 10, the last one, 12 is seal. 5 is the piston, 7 is the cylinder, the cylinder barrel, and 8 is the piston rod. 8 is the piston rod, and the line is the guidance lever, and 11 is the cylinder lead. 11 cylinder lead, and 13 is the dust-proof ring, and the last one is the linear. Makeup cylinders can be further divided into cylinder block assembly, piston assembly, sealing device, cushion device, and venting device. A is the cylinder cover. A is the flanging type. B is the semi-ring type. C is the thread type. D is the parallel type, and the last one is the wheel type. We can see one is the cylinder curve, two is the cylinder barrel, three is the twice length, 4 is the semi-ring, 5 is the stopping latch, 6 is the pearl. Piston assembly. This is the pistons and the rod connection. Whether 1, 2 through 1 to H. piston rod. Q is the piston and seal lock wash and large lift key. 7 is the ring size. 8 is green color. Motion devices. Motion devices. We can see this picture. Big A is the circular cylinder void. B is a circular convoid. C is a variable throttle groove, and the last one is the adjustable throttle orifice. Wind devices. Plastic exhausting elements. Main dimension calculation. The cylinder structure dimension has a direct relationship with the working mechanism of the membrane. Carbon for the tension. On the precondition of proper speed and suitable structural force, each part of the cylinder must be designed according to the related standards. Cylinders should be as compact as simple and convenient to machine install and maintain. Second, the piston rod is essential under the heaviest load. If the piston rod is compression, it should possess a good longitudinal stability when long stroke piston rod exits out. Auxiliary support is needed to prevent the piston rod from dropping. 3. Only one end of the cylinder can be fixed for position for installation or fasteners to ensure long obstruction for cylinder expanding with heat and contraction with cold. Last one, whether the cylinder system needs cushions, venting and combustion-proof devices, all load must be determined based on the correct working conditions. Main dimension calculation, the inner diameter D of the cylinder tube, the diameter D of the piston rod, and the cylinder tube length S. The shortest guide length H. So the intensity check. Wall check sigma of the cylinder tube. In D. In the ratio of chip D to sigma is more than sigma is checked according to the simple formula. The exit point is the permitted pressure, and this is the diameter pressure. When the ratio of P to sigma is less than 10, sigma is calculated according to the formula for the thick wall of the cylinder tube. Can be checked in this equation. Diameter D of the piston rod. Piston rod is of compression. the links of the system calculated where the supposed action shown on this passage the total value where it is the utility according to the related also checking of the depth of the classical system. When the cylinder tube and the cylinder cap are connected by a bolt, the bolt is burst in tension. Under torsion stress, the outforce on the bolt should be amplified by 1.3 times. The bolt must be checked according to the related formula in the material. Is a ring cylinder. Bigger or to gauge the single weight of the cylinder and this will be the balance weight. The leader, the output torque of the swing shaft single weight cylinder can be expressed as this one. With the pressure difference of the valve formula which rate the output with back you still remember this one the torque multiplied the angular meter curve the P out P the power 50 theta P multiplies the flow rate so and the P out ratio of P out the mechanical efficiency multiplies the volumetric efficiency. So we can get angular speed equals E out divide out then E out and E equals this one E and omega and V equals E equals this one this is data. This is the emotions, and this one can. So we can get the angular speed. You can derive the equation in order to open. The videos are in YouTube channel and the copyright to the original, just for education only. So I'll show you the previous.
Hydraulic actuators in aircraft play a vital role in flight and control. Often their operation ensures the safety to the aircraft and every passengers on board. You may not have thought about it much, but if you step into the plane, you are putting trust in a linear actuator. Actuators are used in landing gear, flaps, and in other crucial flight control. Fortunately, these systems are designed with so much redundancy and secondary pathway that a catastrophe great enough to take them offline is likely enough to destroy the aircraft's ability to fly. Famously, United Airlines Flight 232 lost their primary flight controls and were able to crash land. That sounds like an oxymoron. You either crash or land. We are going to discuss this more at one of the remarkable aeronautics facility in Malaysia.
Benefit do hydraulic actuator or weight control have over gas charge unit?
The hydraulic units are much better suited to the extreme temperature requirements of aviation application because they maintain more constant performance over a wide temperature range. For example, such as gas charged landing gears deployment, dampers can become too weak in cold temperatures, causing the gears to slam down into the deployment position. Conversely, perhaps they will become overcharged in very hot conditions, causing the door to overshot of the fully deployed position. A hydraulic unit will form smoothly in both temperature condition, maybe.
Thank you. And can you tell me how many types of emergency landings are there?
All right. So basically, there are three types of emergency landings, which are a forced landing. This is a situation where the aircraft engine fails and pilots forced to land the plane in the nearest airport. So the second one is precautionary landing. This is used when a pilot face a problem due to severe weather condition or big loss in the airspace traffic or due to lack of fuel or expecting an engine trouble. So the other one is ditching. This is where the pilot cannot avoid the situation but to just land on water, which is safer than airborne. Then I will take a landing gear hydraulic system, which is good to for trainer one. As you can see, it has two actuator, the hydraulic actuator, and which is using for the flap and the landing gear. And as you can see, this is a basic hydraulic powered fluid here. So consider the pump underneath, and it drives the pressurized liquids upwards to the filter, and we have a valve side here and the reservoir. So I think we can demonstrate now. So switch on the power as the pump starts to pressurize the liquid, and it stuck on the pump behind this to distribute both to the flap and the landing gear. So now we are operating for the landing gear. So now push it up, and as you can see, once it fully retract inside the wing, so it will automatically lock and the red indicator turns on. Now we're gonna slam it down. That's like that. Yeah, it has fully retracted. So this is a hand pump. As you can see, when the emergency comes, when the landing gear being stuck by the clogged hydraulic liquid, it cannot flow through the hose. So the pilot must pull this up, so it will automatically slam the landing gear downwards. So as we have seen for how the hydraulic actuator works for the landing gear, so it's basically the basic concept for the flaps. So it's using two hydraulic actuators, we see for the front and the back. And these flaps are used to control, perhaps during the takeoff and landing, as it used to control the wind flow underneath as the plane become eligible to maneuver. All right, so I think I will demonstrate now. So the same thing, turning on, and simply drive this pressurized liquid to this actuator. Right? While we're using this perhaps for the takeoff, as the wind flow underneath and it is a lift the airplane upwards. Put it up, and that's how it works. All right, so to achieve this very smooth, precise movement of the actuator, I think is provide more torque, as the hydraulic pump is incompressible rather than pneumatics. So it can work in the extreme cold, the weather condition. So it is doesn't matter whether during a hot or cold conditions, can add very high performance. And so apart from this, we know that actuator is being used massively on the aircraft for the rudder, control the maneuver for the left and the right, the air stairs to extract the passenger during the emergencies. There's many more. There's a lot of hydraulic movement inside the aircraft itself. Right?
Hi everybody, very welcome to Mentor and yet another video podcast. As always, I hope you're doing absolutely fantastic. Today on the video, guys, we're going to be talking about the hydraulic system of the 737. We're going to go through what we do with it in the cockpit, what the indications are, what the components are, and what happens if we lose the hydraulics. Stay tuned.
Wind 31016, Berlin right, right on. Third land, 31 right. Delta 260. Yes, sir, dude.
This video is brought to you together with Blinkist. Now, have you ever found yourself wanting to read so many great books but don't really have the time to do so? Well, I definitely have, and I love podcasts. And right now, I'm using the Blinkist app to listen to a book called The Things You Can Only See When You Slow Down. Now, what's so fantastic with this app is that they have more than 3,000 of our best non-fictional books in its library. And they've sat down and they've distilled those books down to the most important bits, which they call blinks. So this means that you can listen to a book that would take you days to read through in only maybe 15 minutes, which is great. You know, you get the best out of it. And if you want to try this out, you can use this link here below, which is blinkist.com/mentorpilot. You can use the app and try it out for free for 1 week. And if you decide to sign up for it, you get a further 25% discount. So check it out.
One of your extension handles full.
2500.
Train is noted. All right, guys. So the hydraulic system of the 737 is a fascinating system, right? It has a lot of different components to it. And what you can expect from this video is an overview of the system. But first of all, you have to understand why we have a hydraulic system in the first place. So on a smaller aircraft, let's say a Cessna, for example, there's really no need for complicated hydraulic systems because you can connect the flight control surfaces with wires to the yoke or to the pedals. The only real place where you'll find a hydraulic system on these smaller aircraft tends to be to either if they have an extendable or retractable gear or to the brake system. But as you start getting into bigger aircraft that have bigger rudder surfaces and also flies at higher speeds, there start to be a lot of forces put on those surfaces, which means that you need to have some kind of help to move them. There are different ways of doing this. However, the hydraulic system has a very unique way of being able to create the force needed in one place and exert it in a different place, without using bulky equipment where you actually need to exert the force. So for example, we use all of the hydraulic pumps are either in the engines or inside of the central wheel well bay, but the actuators for example, the ailerons or for the rudder is where they are, right? It's out on the wings or back in the tail. And you can exert a lot of force through the hydraulic system component. And very versatile, it's easy to draw and to pull a hydraulic line out to where it needs to be used. So this is why we use hydraulic. However, a hydraulic system is not infallible, right? You can have leaks to the system, you can have pumps not working. So you also have to have, like with every other system on board an aircraft, redundancy. It means that you need to have several different systems that can take up the slack if needed. And that's what we have. So if we look at the components, you have essentially three different main components of the hydraulic system. You have hydraulic system A, hydraulic system B, and the standby hydraulic system. Okay. The way that we monitor the system in the cockpit is we have on the lower display unit, the one that's below the main engine components, you can press a button called MFD, the multifunctional display. Press systems, that will bring up an overview of the hydraulic system. It's very simple. You'll get the system pressure and the system, basically the fluid volume. Okay. The normal pressure that we operate on is 3000 psi. The minimum is 2800 and the maximum is 3500 psi. All right. So as long as we have good quantity, which is on a 1 to 100 scale, generally the amount tends to vary depending on how much we actually use the system. Because if we, for example, have the flaps extended, then there's going to be a lot of fluid from the hydraulic system B out to actually activate the flaps. The system quantity will then go down, but generally it's above 76%. If it's below 76, we're going to get a refill warning. Okay. But warning is only available when we are with normal, but everything retracted and we are on the ground, right? So it's not even armed if you're out flying. Okay. On the overhead panel, we then have the hydraulic panel, which is basically 4 different switches and a couple of lights. Okay. The switches are for each hydraulic pump. So the hydraulic A system has a engine-driven pump, which is driven by the number 1 engine, and a electric motor-driven pump, which is situated in the main wheel well bay. The system B has the same, so number 2 engine-driven pump and an electric motor-driven pump in the wheel well bay. So these are the switches, basically, and during normal circumstances, the engine-driven pump switches are always on, so they always operate when the engines are running, and the electric switches, they are off if the aircraft is being shut down for the night, for example. During turnarounds, we just leave the entire system on. Okay? The lights that you have are low pressure for each pump. So if the system feels that the pump is not giving enough pressure, you get a low pressure. And then for the electric driven pumps, you also have an overheat warning, which indicates that the system, the pump is about to overheat because it's being cooled by the hydraulic fluid. And if, for example, there is a loss of hydraulic fluid and there's nothing going through the pump, it can both lose pressure and overheat quickly. And with that, need to switch off the pumps. Right? Cool. So let's have a look at the different hydraulic systems then. Like I mentioned before, system A is driven by the number 1 engine, the one on the left-hand side, if you see in the direction of the aircraft, and the electric motor-driven pump. There is a difference between these two pumps. They give the same output pressure, so 3000 psi. However, the engine-driven pump gives about 4 times the fluid volume. And this is important to know because if you have, let's say, an engine failure, so you lose your engine-driven pump, it means that the system will still operate, but all of the different components might operate at a slightly slower rate. All right, especially the component that needs a lot of fluid. The flight controls will not be affected, by the way, because they are supported by the opposite system as well. Okay? So, system A, the top part is the hydraulic reservoir. This is where most of the hydraulic fluid is being kept. The reservoir is being pressurized by pneumatic air pressure. That comes from either the APU, if it's running, or the engines. And it's mainly important when we're cruising altitude to make sure that the lower pressure up there doesn't make the pumps cavitate. You need to have a certain pressure on the reservoir. Now, if you look at the schematics, you'll see that in the system A reservoir, there's a standpipe, and that standpipe is connected to the engine-driven pump. The reason for this is that if you have a failure of the pump, a leak in the engine-driven pump, well then the hydraulic fluid will be going out, will be disappearing, but only down to the standpipe level. And below the standpipe level, the fluid taken to the electric motor-driven pump is still available. So this means that if you have a leak in the engine-driven pump on the left-hand side, the hydraulic A system is still available through the electric-driven pump. And then you'll see that there is a hydraulic line going to something called the PTU, the power transfer unit. That's because system A fluid is being used to drive a motor that pressurizes system B fluid in case you need to use the power transfer unit. The power transfer unit is really only there to provide extra volume to drive the leading edge devices and the standby the leading edge devices in case they're needed, for example, for auto slat extension in case of a low speed scenario, something like that. So it's a kind of a backup to make sure that the amount of fluid in the hydraulic B system is available, even if you would have, for example, an engine failure of engine number 2. All right? And then, as you can see, the hydraulic A system is being connected to all of the flight control surfaces, so the ailerons, the elevators, and the rudder, but also 2 of the flight spoilers on each wing and the ground spoilers. Okay, it's connected to the autopilot A. So if you have a loss of hydraulic system A, the autopilot A will not be available, but the autopilot B will be. And also the extension and retraction of the landing gear system. Right? Now, as you can see from the schematics here, there is no other connection to the landing gear extension or retraction, which means that if you lose system A for whatever reason, well, then you need to have a separate standby system to extend the gear. And we do. We use the alternate extension system, which essentially is just using gravity to let the gear fall out by themselves. There is a specific checklist for that, and it entails basically just opening the up locks. I have done a separate video for that. If you haven't checked it, I have a cockpit video for how you do that and how we do the entire checklist, which you can check out up here. All right, it's really good. Then, if you go over to hydraulic system B, you'll see that in the system B reservoir, there's also a standpipe, but this standpipe is feeding both the engine-driven pump and the electric motor-driven pump. So this means that if you have a leak in any of the pumps for the system B, the fluid level will drop down to the standpipe and you lose system B completely. But below the standpipe, you have the PTU. Right? So the power transfer unit will still have volume for system B, even if that happens, to drive the auto slats. Right? Then if you go down, you'll see that the system B is backing up the ailerons, the elevators, the rudder as well. But in system B, you have the trailing edge devices as well. So the trailing edge devices, if you lose system B, will not have system A pressure to get them out. So we have an alternate extension procedure for that, using an electric motor to drive the screws that will extend the trailing edge devices. However, it is much slower and it doesn't have the same skew protections and protections in general as a normal system does. So you have to be very careful if you use the alternate trailing edge flap extension procedure. Okay. Then it's also connected to 2 of the flight spoilers on each wing and to the autopilot B, of course. But it's also being used for the landing gear transfer unit. So this is a similar situation to the power transfer unit, but it's different in the way that the system B is being used is it actually gives extra volume. If you need to get the gear up, and you get an engine failure after takeoff on engine number 1, for example. Remember I told you that the engine-driven pumps gives 4 times the volume from the electric one? Well, we understand that if you have an engine failure on engine number 1, you want to get the gear up, you want to reduce the drag as quickly as possible as part of an engine failure after takeoff scenario, well then you need to get the gear up fairly expeditiously. And in this case, the landing gear transfer unit jumps in and it gives the additional volume to get the gear up as quickly as possible, to reduce the drag and to get the aircraft climbing away. So it's a very, very smart system. Okay? And then you have the standby system. Now the standby system works to kind of pick up the slack from, for example, the thrust reversers. So if you have a failure of system A, well then the normal thrust reversers are not activated, but the standby thrust reversers are, albeit at a very slow rate. So you might get one thrust reverser opening up quickly, the other one slower using the standby system. So that might give you a bit of a yaw of the landing. So you need to be aware of that. It also activates the leading edge extension. In case of loss of system B, it drives the rudder. In case of complete loss of hydraulic system, which we'll get to in a second, and the standby yaw damper also in case of a complete loss of hydraulic system. All right, so it's a smaller system, but it comes in and kind of picks up the slack where it's needed. All right. So what about failures then? Well, we've kind of touched on it a little bit already, but I just want to highlight a few things. If you have a leak in a system component in either of the systems that is downstream of the pumps, you are likely going to lose that hydraulic system. But as I've indicated already, it's not that big of a deal because all of the really important functions are being picked up by the other system, for example, how to control the aircraft, or by the standby hydraulic system. There are, however, some things that will not be taken up. For example, there is no additional hydraulic source that will drive the autopilot. So if you lose system A or system B, that autopilot channel will not be available for you, and that will be important if you want to try to do an autoland. Because remember, you need 2 autopilots to do an autoland, and that will not be available to you. So that will be important from a planning point of view. And then you have specific parts of the system that will not be activated hydraulically. So in the case of a loss of system A, for example, you'll be able to continue to fly the aircraft perfectly. You just use autopilot B instead. But then as the pilot monitoring reads through and executes the curate checklist, there are some things that will be highlighted. For example, you need to plan for a manual gear extension. The reason they say plan for it is because it takes a while to do. Doesn't take long, but it takes maybe 30 seconds. While normally just lowering the landing gear is something we will do maybe at 4 nautical miles. It just takes a second to do. Here it maybe takes 30 seconds to read through, so you might want to plan to do it a little bit further out. And also, since you're now using the kind of gravity to extend the gear, there is no hydraulic system to actually take the gear back up in case you need to. So this means if you do a go around, the gear will be hanging out, you'll be climbing slower, and also if you do a go around because of poor weather and you want to divert, you will not be able to get the gear up during the diversion, which means you're going to use a lot more fuel. So this is something that you will have to plan for as well. Maybe choose to go to a destination which has good weather that can, assure a landing, or if it has really marginal weather, maybe think about doing a diversion. Also, on top of that, you have to input into the OPT, our performance tool, that you have a loss of system A, because things, for example, like the ground spoilers are not activated anymore. So you'll have a longer landing distance. All right? The same goes if you lose system B. You're losing certain components. Most of them are being picked up by system A, but the trailing edge flaps are not. Okay, and neither are the leading edges, which are now being run by the standby system. And the trailing edges, you'll have to drive them out using an electric motor, which you'll actually have to hold down to make sure that the trailing edges comes out, and you basically just let it go when you have the trailing edge you want. And as the trailing edges comes out, the leading edges will be automatically extended depending on what flaps you're using, but you will not be able to retract them. Right? The standby system is only extending the leading edges, it will not retract them. So once again, you're going to have to think about that in case of potential diversion from a fuel burn point of view. Okay? This will also take time, so maybe give yourself a slightly longer final, slow things down a little bit, monitor the trailing edges very carefully to make sure that there's no skew or anything happening during the extension. But all in all, not a big deal either. All right? Now, the real problem comes if you find yourself in the very unlikely scenario of a loss of both system A and B. Now, there is a checklist for this as well. It's called manual reversion. And the reason it's called manual reversion is because you are now going to have to go in to actually handle the 737 using muscle power. Remember how I talked about the Cessna before and how you use wires that are connected to the yoke and to the rudder pedals in order to drive the flight controls? Well, essentially, if you lose both system A and B, you're turning the Boeing 737 into a big Cessna. The 737 is one of the only aircraft of this size left that actually have physical wires connected out to all of the flight controls. So if you lose system A and B, the rudder will still have some hydraulic help from the standby system. You will still have a standby yaw damper that will work, but ailerons, elevator, that's all by muscle power. So you need to be careful. You need to plan this really, really carefully, guys, because you don't want to go into normal, maybe 30 degrees bank. That's going to be way too much. It's going to take you way too much muscle power to get it back level. So plan for maybe 10-15 degrees of bank, which will give you much bigger turning radius. So in this case, plan for a really long final, right? It's going to be a struggle to do this. You can think about things, for example, about changing roles, so that if you have a long way to fly to your destination, and then as you're starting to kind of wane with muscle power, switch over so that the pilot flying can rest, and make sure that you have someone who's well rested to actually fly the approach procedure in itself. All right, it'll be perfectly controllable. I want to really emphasize this. Like, the 737 is possible to fly with these wires. It's not like an Airbus that requires a ram air turbine, a RAT, to be extended in order to get hydraulics back. It can be flown like this, but it is a bit of a struggle. And remember, once you get down on the ground and you land this thing as well, now you don't have any flight spoilers, you don't have any ground spoilers. So the landing distance will be longer, and also crucially, you don't have neither normal nor alternate brakes. Okay, so the brakes that you'll get from what's left in the brake accumulator, which has some pressure in it. It always saves a certain amount of pressure so that you can get some braking, right? But this brake pressure accumulator, it only has so much pressure, so you cannot be pumping the brakes. If you do, you'll be running out of that, pressure that's left, and you might find yourself without any brakes whatsoever. So once you land, one steady application of brakes until the aircraft is completely stopped. Once you are stopped, remember, you don't have any nose wheel steering. You will not be able to taxi the aircraft. So it's just about hoping that you have enough brake pressure in the accumulator to set the parking brake, and then just wait for a tow to call and tow you to your final destination. All right? So basically that's it, guys. Like, this is the hydraulic system. It's a very, very good redundant system with a lot of backups in it. And even if you fail completely, you will still be able to fly the 737. It's a great aircraft from that perspective, okay? Now, I'm guessing that you probably have a lot of questions about this. As always, put them in as comments below. I'll try to answer them there. But if you want to talk to me directly or to other operational pilots, either on Airbus, Boeing, or on a private jet, or whatever it might be, we have a lot of them available inside of the chat of the Mentor Aviation app. So once again, this app is completely free to download. You have the links to download it down here. Check it out. Just tag @Mentor if you want to send me a message. And that's it. I want to send a huge thank you to the sponsor of this episode, which is Blinkist. It is a really, really good app, which I use myself a lot. And if you want to try it out, then just use this link here below. You'll get 1 week where you can try it absolutely for free. And then if you like it, you get a further 25% discount by using this link on the price of it. Okay? So,
老师，老师。
The last one is our assignment. Our assignment. Question 1, assignment question 1 have is in chapter 3, and we have done it in last class. And then we have assignment 1, question 2. This is question 2. This is question 3. Last one is question 4. Requirement is do the assignment 1 by yourself and write in handwriting form. And scan your handwriting and send it to my mailbox before April 14. Now you can do your assignment.
OK 老师。 老师 are you hearing me 老师
I can hear you. What's
yeah
the
老
problem?
师 basically I'm not clear about the question. Could you please explain a little bit the question, please?
Which one? Which one? Question one
Number
or two?
2, 3, 4, even 1. Yeah.
Yeah. Mm, the flow rate and pressure can be calculated by the equation we have described in the slide. By these equations. This by character parameters. This one to one to the this one, and you can according to the working condition or the you can calculate the flow rate and pressure. This one also the property of the rotation speed. This is a bit different. I can tell you later. This one, this two, this one, and this one can be calculated according to the slider, the former slider. And the last question, we should use the knowledge we learned in chapter one, and you can also find the equations in chapter one, and then you can calculate the working pressure and the speed. So the last things left for you to think.
It's a little bit hard.
So actually, it's very very difficult. So
Right. Let's see.
please pay attention to unit, the unit here and the unit. You should change into the standard unit. See, such as in this equation, the unit n is unit a unit n is load, and in this equation, this equation, unit is load. You should translate this unit to this. Go back to the slide. when you finish your sign work, you will get the whether it's right or left, you can get relative high scores for assignment. It's nice you have did it. Okay, today class is over. Thank you everyone.
Okay, 老师
Okay, class is over.
Thank you 老师